All right, so this is going to take us through the Free Response 2011, number 5, dealing with differential equations. So this is number 5, which means it is a no calculator question. So we're going to do all of this without our calculator. I'm going to go through each part individually, but I first just want to do a quick preview of the question, which is what you really should do when you get started on a free response. So to start, it says, at the beginning of 2010, a landfill contained 1,400 tons of solid waste. So in 2010, we had 1,400 tons. The increasing function W, well, if a function is increasing, that means W prime is greater than 0. Models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation dW dt equals 1/25 W minus 300 for the next 20 years. W is measured in tons, T is measured in years from the start of 2010. So I am good to put a 0 here, representing 2010 as our start year. Use the tangent line. Okay, well, I know how to write a tangent line, right? That's just going to need a point and a slope. Find d squared W over dt squared. Well, that just means the second derivative. Okay. Find the particular solution. So this will be where I separate my variables. The reason why it's important to read through each one of these in their general what you are looking for is a lot of students just dive right in and do this. But we don't need that until part C. We're not even going to look at separating variables and taking the antiderivative until we actually need to find the particular solution. All right, so let's go ahead and look at part A. Use the line tangent to the graph of W at t equals 0. Well, before I can use the line tangent to the graph to approximate things, I should probably find the line tangent to the graph at t equals 0. So I need a point, 0, comma, and I had 1,400 as my initial condition, and I need a slope, so I need dW dt when t is 0. Well, dW dt is represented by this differential equation, so that's going to be equal to 1/25. My W at time 0 was 1,400. So if I continue to clean this up, I have 1/25 of 1,100. You can go through and actually do your long division there if you want to, but you can also think there's 4 quarters in a dollar. So if I go through and I do that whole thing, there's going to be 40 quarters in 1,000. So then another 4 will be 44. So our slope at time t equals 0 is 44. So putting those together into the line tangent, I'm going to have W minus 1,400 equals 44, my slope, times t minus 0. Okay, so I'm using the variables that they give me. Remember, it's important to work in the variables provided. And then we're supposed to approximate the amount of solid waste at the end of the first 3 months when t is 1/4. So I'm going to use this line and I'm going to plug in t is 1/4. So W minus 1,400 equals 44 times 1/4 minus 0, which is really just 1/4. So W equals 11 plus 1,400. So there are approximately 1,411 tons at time t equals 1/4. So remember, we were using a tangent line to approximate something nearby 0. Okay. Part B, find the second derivative in terms of W. Use the second derivative to determine your answer if your answer in part A is an underestimate or an overestimate at t equals 1/4. So it says we're supposed to use the second derivative. So let's start by finding it. I'm going to take this first derivative. That's a dW. dt equals 1/25 W minus 300. So I'm going to take the derivative here with respect to time. So this, I get the second derivative of W, and then dt squared equals 1/25 is just going to hang out. It's a constant. The derivative of W with respect to time is dW dt minus the derivative of 300 with respect to time is 0. So you can write it, but you don't have to. And then from my original information, I know that dW dt was really equal to 1/25 w minus 300. So I just took this and applied my dw dt. If I want to clean that up a little bit, d squared w over dt squared equals 1 over 625 w minus 300. And then there's a couple of ways that we can go about doing this. If we want to know if a tangent line was an overestimate or an underestimate, we care about the concavity. So if our graph was concave up, then tangent lines are underestimates. That didn't draw through like I wanted it to. If our graph were to be concave down, then our tangent lines are overestimates. So two ways you can think about this. Using this cleaned up version, we know from our given information that w is always greater than or equal to 1400, because that's what we start with, and w is strictly increasing, in which case the second derivative is going to be a positive number times at least 1100, which is positive. So this whole thing will be greater than 0. Therefore, our tangent line, if our second derivative is greater than 0, means our graph was concave up. So our tangent line is an underestimate of the actual tons. The other way that you can do this is if you didn't want to have to sub in dw dt, we knew that dw dt was always positive. That was one of the things in the stem of the question. Your function was always increasing, in which case dw dt, always being a positive value, no matter what you pick for it, times another positive value is still going to end up with the second derivative being greater than 0, which still confirms concave up, which still implies the tangent line is an underestimate. Okay? I think that's it for B. And then part C, the one that everyone likes to just jump to. Find the particular solution W. Okay, so W has to be by itself. That's important there. To the differential equation with the initial condition W of 0 equals 1400. So remember, our steps for these ones are always to start by separating our variables. I'm going to write this out. You don't have to actually write the steps. So dw is going to stay on the left side. I'm going to multiply the dt to the other side. And I'm going to divide by w minus 300. So I separated my variables. Step 2 is to take the antiderivative. And remember, you do that through whatever means are necessary. So on the right side, I just get 1/25 t plus c. On the left side, technically, I need a u sum. So u is going to be equal to w minus 300. du is a perfect match with dw. So I get the integral of 1 over u du. But also in your head, you might be able to do that because you know that there's not going to have to be a adjustment there. So I'm going to get the natural log of u equals my 1/25 t plus c. Okay, so I separated my variables, took the antiderivative. Step 3 is apply your initial condition. Ooh, technically make sure you have your plus c. Then we're going to apply our initial condition. So the natural log of 1100, because w is, those can be parentheses now because we have the positive value, right? 1400 went in, equals 1/25 times 0 plus c. So we just found our c is equal to the natural log of 1100. I'm going to write that a little clearer. And then step 4, I'm running out of colors. Step 4 is to solve for, in this case, w. So I'm going to go back to the natural log w minus 300 is equal to 1/25 t plus the natural log of 1100. In thinking about the absolute value bars, we know that whatever is in here is going to be a positive number because W is greater than or equal to 1400. We're talking about tons for W, and we wouldn't ever have negative weight in terms of the tons. So from a real world application standpoint, we know that we're good to drop those absolute value bars. So I'm going to do the E on both sides. And remember, this will end up being E to the 1/25th t plus the natural log of 1100. Keep writing 1,000 instead of 1100. So continuing to clean that up, W equals E to the 1/25th t times E to the natural log of 1100. There was a video about that earlier. Plus our 300. This then will cancel. And so remember, that becomes like our C E to the KT. Remember that part of our video? Plus 300. And that is our final answer. We have solved for W, which is equal to W of T. You can always test your answer. If you were to plug in 0 here, you would get E to the 0, which is 1, times 1100. 1100 plus 300 is 1400, which was our initial condition. So again, in thinking about these types of questions, please read through each part at the very beginning. Don't just jump in right away and start to separate separate variables because you see the dw dt. You want to make sure you're actually reading what the question is asking. And we only do the separation of variables when it says find the particular solution, or sometimes it'll even say separate the variables to find the particular solution. Okay, so that one should be pretty straightforward. You can look at the scoring rubric online and see how we did, but we did things correctly. I think that would be a 9 out of 9 for us. All right, let us know if you have questions.